www.nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
We'll get started on lecture 12. This is on equilibrium concentration of electrons and holes in a doped semiconductor. Now remember, from the very beginning of the course, I had been emphasizing the fact that I need two things to calculate current. One is electron number, and the other is velocity at which electrons move. And for the electron numbers, we first took a wrong turn. We just looked at the crystal, number of atoms in a crystal, and just tried to multiply with the number of electrons a particular material has, and we saw that that really doesn't work in terms of conductivity of the material. So we went through this quantum mechanics and statistical mechanics, Fermi-Dirac statistics, density of state, and finally we are in a place where we can consistently explain how many carriers I have at any given temperature in given material, and that's really fantastic. Until 1940s, perhaps even 1950s, despite all the development in physics, what you are going to learn today and what you probably learned yesterday in the last class, people couldn't do. So these are actually in some sense very advanced and sophisticated calculations. So we'll see. But actually now in retrospect appears quite simple. We'll talk about carrier concentration, but the point I want to emphasize today is the temperature dependence of carrier concentration, because we'll see that although at room temperature, it's very difficult to get carriers on in the conduction band and get good conductivity. If you raise the temperature, you can see that the electrons will jump from the valence band to the conduction band more easily, right? It has more energy, and that will dramatically change the conductivity and or the carrier concentration for that in this particular case. So we'll look at that. We'll also talk about multiple doping and co-doping, and I'll explain what they mean, and the heavy doping effects, these three things, and finally conclude. Now, this is something I have discussed in the previous lecture, that in any semiconductor, let's say silicon, for example, if I dope it with a certain amount of boron, which is a p-doped material, acceptor, and let's say a certain number of donors, like phosphorus, then I will have a change of carrier concentration from the intrinsic value. Intrinsic value is very small, right? 10 to the power 10 in silicon, out of 10 to the power 22 atoms. Humongous free spaces, but let's say if you dope it, Nd and Na, then we can calculate the change in the carrier concentration. We said that if the material is doped spatially homogeneously, that means on the average, uniformly dope the whole thing, then not only it's globally charge neutral, the P and N, it is locally charge neutral also. That if I go in a micron by micron, micron square by micron square, micron cube by micron cube, I'll see that locally it is charge neutral as well. And we wrote those four expressions. Now, only thing you will see that's slightly different from the previous lecture is that instead of writing the simplified expression for the holes, I have written the whole thing. You see NV, the Fermi integral of half and everything. Correspondingly, you have the, I'm sorry, this should be an NC. This is a typo, I'll correct it. NC and then the rest of the terms. Now, this is the full expression. If you solve this, and the only unknown here is the Fermi level EF, you see everything else is known. If that is solved, then actually I'm done with my problem. I could go home. But the thing is, you can see that this looks a very complicated thing. First of all, I have Fermi-Dirac integral, capital F half in one side, and then I have all this Fermi-Dirac-like functions on the right-hand side. It looks complicated. And I mean, it just visually looks complicated. One quick thing I want to point out, why on the one side there is Fermi-Dirac integrals, and why on this other side just Fermi-Dirac function? Because in one case, you see, I had continuum states. So I integrated them over them, right? Because I wanted to see how they are all occupied. For the donors and acceptors, I assumed a single level. So I didn't do any integral. So therefore, you can see in two sides, I have slightly different functions. Okay, that's no rocket science. And then, of course, if the Fermi level is significantly below the conduction or valence band, or away from the conduction and valence band, about 100 millielectron volts, let's say, then I can make this approximation. But how would I know? You know, I haven't solved for EF. How would I know where is it, right? The best way to do it is to start from the simplified expression in the bottom. Solve for the EF, the Fermi function EF, because that's relatively easy. And then you check the argument that is it below 100 millielectron volts from the conduction and 100 millielectron volts above the valence band. If it is, then I am done. If not, then I go back to the top expression because that's more accurate, right? And that will always apply. So that's more accurate. Okay. Now, my goal is to calculate EF, and then that will allow me to calculate everything. N, P, the electron hole density, donor acceptor, I'm done actually. I can do a lot of things. So the purpose of today's lecture, at least for maybe 10, 12 slides, is just to show you how to calculate it. In principle, you could read it yourself. It's so simple, but I will help you to guide you through. It's not, the next few steps are not conceptually difficult at all. It's just a few algebraic steps. So let me help you along on that. So the first point is, does this expression, which we just said, reflect what we did previously without making this argument? For example, one thing we said, that if a material is undoped, then I should not have any donors or acceptors, right? Undoped. So I don't have them. And so that's gone. So in that case, you see, in that case, only the first and the second term remains. N minus P equals 0. I can equate them, and I can then solve them for the Fermi level EF. And once I solve them, this is exactly the expression we did before. Remember, this is the intrinsic semiconductor. Of course, the more complicated expression will reduce to this very simple formula when I remove my acceptors and donors. No problem here. And once you have EF, you could easily calculate the value for N, which is now the intrinsic carrier concentration, 10 to the power 10 per centimeter cube, and correspondingly also the value of holes. Now, when you have doping, of course, things are a little bit more complicated. So let's see how it works. Let me assume a case where it is N-type. When somebody says that I have a N-type semiconductor, what they mean that they have only donors that gives away electron, so that the material has a lot of electron, right? So that's why it's called N-type material. And in that case, we will assume that there are not too many acceptors, right? Too many, Na is approximately equal to 0. That I have not put any boron in. I have only phosphorus in. And correspondingly, you could do the whole thing for P-type doping. Okay, so you see, if I don't have any acceptor, I should get rid of that term, right? I should get rid of that term. And you remember that the term I have shown here in red circle, I've circled this. This is actually N written in a slightly different way, more expanded function. Okay. Now let me assume the problem has been solved. So you put it in a MATLAB function or you somehow solve it. I'll also solve it in a few minutes. But let's say I have solved for EF first from this expression, only unknown. And I have inserted the value of EF back in to calculate the value of electron concentration. Let's say I have already done that. If I did that, this is what I'll be saying. What I have shown you here in the y-axis is how many electrons I have as a function of how many donors I put in. Let's say I put in 10 to the power 18 number of donors, phosphorus, N, and silicon, and I have 10 to the power 14 number of electrons. So on this plot, it will be 10 to the power minus 4. So there will be a point in 10 to the power minus 4. In general, if I take a temperature as in the x-axis, I will see a plot something like this. That at very low temperature, the number of electrons will be minuscule even when I have doped it. You see, this is not intrinsic, but even when I have doped it, still it's very small. Somewhere in between, you see in the intermediate temperature range, and that changes with every semiconductor, I have the number of electrons equal to the number of dopants, as if approximately these two numbers are the same. And finally, at some point, the number of electrons becomes larger than the number of dopants. Now, how can that happen? I put some dopants in. How can I have electrons which is larger than this? We'll explain in a second. And there are, in principle, if you solve the equation in the previous page in a computer, you would have gotten the whole curve in a single shot. You just put the temperature in and get a Fermi level out. Put a temperature in, get the Fermi level out. And you could have plotted the whole thing in a MATLAB function in a single call, the whole thing. But if I wanted to do it analytically, then it's better that I, put it in different chunks so that I can solve them easily. So one region we'll be calling it freeze out. I mean, in Indiana, looks like this is the appropriate region of operation. The other part we'll call extrinsic. The yellow part you see, we'll name it extrinsic, where the electron concentration is approximately equal to the donor concentration. Now remember, this is the part I want my device to operate on, right? Most of your computer, if you take it to Alaska, that will be in the freeze out region, let's say. Or if you take it for a solar mission, then it will be on the right-hand side, let's say, which would be the intrinsic part. Now, the most of the time, I really want to, when I design a computer or design an IC, I want to make sure that my devices really work in the extrinsic region, the yellow region, not in the green or in the blue part. And what happens in the extrinsic region, that although you had a lot of dopants in the beginning, but if the temperature is high enough, let's say 600 degree Kelvin or 700 degree Kelvin, let's say very high, and this can routinely happen when you have, by a computer, sometimes if things are not properly grounded, if you touch it, then the ESD pulse, just like when you touch a doorknob, the amount of voltage that can flow in the transistor can be huge. In fact, in that case, temperature rise can easily be several hundred degrees C. Of course, it will destroy the computer. But if the temperature rise is significant, in that case, the number of electrons from the valence band will jump to the conduction band. And let me show you some pictures. And in that case, that will take over. So let me explain. So in the freeze out region, all the dopants are there, but it at least need about 100 millielectron volts to donate, right? It's bound level. Remember the hydrogen levels? If you don't even want to give it 100 millivolts, then nobody is giving any electron. And therefore, there will be no dopants, no dopant will do nothing, right? You haven't given any temperature. So let's say 10 degree Kelvin. So you don't have any electron. Now a little bit later, when you increase the temperature a little bit more, then you'll see the donors will easily give out electrons to the conduction band because it needs only 100 millielectron volts. But there'll also be a few from the valence band. Valence band will be few. Why? Because it's such a big jump, 1 eV or so in order to jump up. So therefore, in that region, it will be approximately equal to whatever number of donors you have. Right? Now, if you went farther, increase the temperature even more, well, donors have given whatever they could. Remember, in the valence band, what is the effective density of state? On the order of 10 to the power 20. Lots of states there, lots of electrons. So when you increase the temperature, if it could give all the way jump up, it could actually give huge number, much higher than what donors can give, right? So at some point you can see it can easily overwhelm the number of electrons from the donors. And that's why the Ni of the material can exceed the donor density, and that's when it takes over and it's no longer a doped semiconductor per se. It's like an intrinsic semiconductor, because as far as at that temperature electron density is concerned, it doesn't know about donors at that point, you see. Okay, so these three regions, let's try to make some calculation. How many? How to get that curve analytically. So what I did here in the first one, you know this, that N is by definition effective density of state about 10 to the power 20 per centimeter cube multiplied by that beta is 1 over kT, by the way. Anytime you see beta in this one, EC minus EF depends on where the Fermi level is. So you can rewrite it. You say NC e to the power beta EF on the right hand side, and you can flip the capital NC and EC on the other side. Okay. Now you also know this, right? Do you know this? ND plus is ND1 plus 2. You remember 2? The degeneracy factor. Where did that come from? Because I had one bound level talking to one conduction band. That's why I had 2. If it talked to 2 valence band, I had 4, right? That's that 2. And E sub D is the donor level. Remember 100 millielectron volts below the level? So that's what I have. But you see, I also have in the magenta, I have shown an EF, but from the top expression, I could replace that. All I did, you see, from the top expression, the magenta EF, I have replaced it in the bottom one. Now look at this expression carefully. What is unknown in here? That the EC is known, right? Conduction band. E sub D is a donor level, known. NC, effective density of state in silicon, I know that. So in fact, if you look at it, except for N, that's actually a constant. I mean, I know ahead of time for the material. So I will write it, everything that is known already, in N sub xi. Now, of course, this is a material dependent constant. For silicon, it will be 1 N sub xi. For germanium, it is a different N sub xi. And the effective quantum mechanics and everything is hiding through N sub c. Effective density of state has effective mass, right? Effective mass knows about quantum mechanics. So all those are hiding in this little N sub xi. Okay, so from here, I can calculate. Look at this. That's the full expression. I don't write Na minus because it is a N-type material, right? I don't have any acceptor. Now, do you agree with this statement? I have written the previous one in the expression below, and it has a several tricks that you should remember. The first one is this. You see the first term on the left-hand side that goes with the valence band and the number of holes, that expression, P multiplied by N on the left-hand side equal to Ni squared. Anytime you have a device, doped or undoped, but in equilibrium. You see, I haven't applied any voltage here, right? Doped or undoped in equilibrium, that one is always correct. P multiplied by N. And so you can see, in order to get the value of P, I can simply write Ni squared divided by N. No problem, right? Second one, well, N is N, no problem. And the third one I just derived. Now, this is a equation. The only unknown here is N. And if I somehow can calculate N, I can go home. So far, there's no approximation, but that's not really true, right? Because the law of mass action, how did I derive that? I assume the material is non-degenerate. Do you remember? I multiplied this P expression and N expression, and I got Ni squared only when the material was non-degenerate. So that is an approximation already built into it when I came here. But other than that, I haven't done anything so far. So let's look at the freeze-out region and see why it goes like this. Let me assume, first of all, it's a donor doped material. So it has a lot of electron actually, and not as many holes. You would assume that. And we'll check that in a little bit. So we'll drop the first term just to get started, assuming the number of P, the number of holes is small. And we'll check that. Once you have done that, drop the first term, Ni squared divided by N on the top equation. Then you will get something simple, and you can see that will lead to a quadratic equation for N. n squared plus nxi multiplied by n and the whole thing. And once you solve for it, you'll get a expression like this, which goes with nxi and the number of donor density. Now, don't worry about these things, right? This is so simple. Don't even have to think about it. Now, after you have calculated n, however, from this expression, you should put it back in the original expression with ni squared divided by n to check whether the p, the number of holes, is indeed small or not. It will be. But whether it's not correct or not, that assumption, you should check. Okay, so I'm done. And in the freeze out region, if I just plot this expression out, I'll be able to get the first part of the curve. That is something you can easily put it in your computer and see how it works. By the way, where is the temperature? Where is the temperature in this expression? It is in n sub xi. Why? Because n sub xi has effective density of state sitting in there, right? Do you remember? And effective density of state is density of state, which is temperature independent, multiplied by the width of the region which was occupied, and that changes at every temperature. So the place where the temperature is hiding in here, and why that gives you that particular curve, is because n sub xi is temperature dependent. Okay. So we could plot it out, and it's not a problem. Now, what about the transition region from the freeze out to the extrinsic? Well, in that case, we can take this expression, which we just looked into, and sort of look at its behavior at higher temperature. That where does this curve go at the end of the freeze out region? What I have done from the step on the top to the step on the bottom is I have assumed the number of donors is actually smaller than n sub xi. How do you know that? N sub xi you can easily calculate, and because at every temperature you can calculate it, and nd is some value that you put in by hand, right? The number of dopants you put in. So you expand that term and you can see the factor half, which was under the square root, that becomes on a Taylor on a binomial expansion, becomes a half up front. Now, do you see that what this value is going to be? 1 will cancel. Do you see that? Do you see that the other piece will cancel also? This n sub xi will cancel, and this becomes equal to n sub d. Do you see this? And only at that point, the n will become equal to nd. Now, there is no insight here. You see, I just did a math, few lines, and no insight. But the point you sort of can see, as you're raising the temperature, right, n sub xi will get larger, and as it gets larger, then you'll be able to make this expansion, and then that will equal to n sub d. Right? What happens at lower temperature? You see, at lower temperature, what's going to happen, n sub xi will be a smaller number. If it is a smaller number, you will not be able to make that expansion. And when you cannot make that expansion, you will see the carrier concentration going to 0. Right? So this is something you should check it out. Okay. How will you calculate the hole density? Anytime you know the electron density, always use this mass action rule. N multiplied by P is Ni squared. In equilibrium, remember, because we'll see many examples where it's not true anytime you apply a voltage. Okay, so we just saw this ND. Again, once you know the temperature is large enough, then that factor EF minus ED, is it a positive number or a negative number, you think? EF is, if the whole quantity is negative, you can see at large enough temperature, the whole factor will go to 0, or the whole exponent will go to 0, and therefore the whole factor, no, it will go to minus infinity, and the whole factor will go to 0. So you should check that step out also. The whole term should go to 0. And again, you have the same expression, but this time because the whole factor goes to 0, you can throw out the denominator, replace it with 1. You see this? That once you do that, again you have a quadratic equation, and once you have the quadratic equation, you can solve it. See? So once you know this ND, value of ND and Ni squared, you can calculate, once again, the value of the electron concentration in the yellow region. Now this part is sort of just math. There's no physics in here, but I'll just lead you through. So what happens when ND is much, much greater than Ni? When can that happen? When the temperature is low enough so that the number of electrons from the valence band do not jump to the conduction band as easily as the number of donors I have. If I have that, assuming, then do you agree with this statement that N will become equal to ND? Ni squared, you drop it. And therefore, they take the square root, and that gives you ND. Do you see that? ND over 2 plus ND over 2. So I will have ND if it is much larger than the intrinsic concentration around here in this space. Now what happens if my temperature is very high, very high? In that case, temperature is very high means lots of electrons are going from the valence band to the conduction band. My Ni is bigger than Nd. And in that case, do you see why? Because Nd is negligible compared to Ni squared. Take the square root. I'll have equal to Ni, and that's when this intrinsic carrier concentration will exceed the dopants. And in that case, the material will become intrinsic once again, even in the presence of doping. Now, the reason why this is a very important discussion is because many times, let's say you work for NASA, and you are asked to design an electronics during the liftoff period. You are asked to design an electronics which will survive the high temperature during the process. Either you can insulate it, of course, but if it is somehow exposed to high temperature, then let's say you designed a computer just fine with all the dopants, with the carrier density, everything working at room temperature. But as soon as it goes to higher temperature, you can see, because there is so many electrons going to the conduction band, the whole thing will become intrinsic again. Your transistor is no longer a transistor, because all the doping, all the design you did, those are all gone. And it is just a chunk of useless silicon. And of course, your computer isn't going to work. So high temperature electronics, many times in the furnaces and other places, when you want to design this, silicon will not work. 1 EV is simply not large enough. So people here, there are professors who spend their lifetime working on silicon carbide, for example, a little bit larger bandgap material. Lots of people use, you'll see if you look at professors' interest, they will say high temperature electronics, and then the material they list next to their interest, you will see always has a higher band gap. So therefore, the range of temperature they remain in extrinsic is much larger, because of course electrons cannot go up that high as easily. And that is how, depending on the operation or depending on the use condition, the material that to be used will be different. Okay, this is an important point. So if I give you an exam problem or a homework problem in which I specify a temperature and ask you to calculate this, you shouldn't always put N equals Nd immediately and start doing the calculation. In the undergraduate years, you could do that, not now. Okay, so once you know N, that's what you did last few slides, right? Solve for N. Once you know N, you could calculate EF, because EF and N have one-to-one relationship. And once I know EF, I know hole density, I know donor concentration, I know everything. So I'm done actually, I can calculate everything. And then if I apply electric field, electrons will begin to move from here. Now, the points I wanted to make, a few points. So, I'm done with simple undergraduate level discussion about how to dope, how to calculate the number of electrons, and I'm essentially done. But you should be a little bit careful about a few more things, because I made a series of assumptions which may have escaped you. The first is, nobody says that you just have to have one type of donors. In principle, in a given material, you could have two donors, two different type of donors. Now, if you have two different type of donors, let's say phosphorus and something else, some other material, then you will have not one level, you will have two levels, right? Red and blue, both will give electrons. How would you solve for that problem? Just by generalizing this a little bit. So, what I have, if they have equal amount of doping, then I have Nd, but you see I have a Ed1 in the denominator of the third term shown here in red. That goes with the donor level of that trap, right? What about the blue one? Well, this time I have another term, which is the fourth term from the bottom, in which I have E sub D2, because the electrons have to jump from conduction, from the blue level to the conduction band. So I will have to introduce another term here, right? So in general, if I have multiple levels, I will just add up multiple levels here. And then I'll again, you see only unknown here is, what is unknown? EF. Everything else I know. I will again use exactly the same procedure that we just discussed and calculate the electron number, whole number, and everything. Now, ND, two NDs I have shown here on the third and fourth term, I have assumed them to be equal, need not be equal. If they are not, ND1, ND2, and you can see how it works. Now, this is, if you have multiple levels, I'm sorry, I have to backtrack on this one. So this is a multiple levels of the same donor. That's why I have kept this two NDs the same. Because if I have just phosphorus, let's say two levels if I had, phosphorus doesn't have two levels in silicon, let's say, in that case, I will just do it because I have the same number of donors. But if it is co-doping, co-doping means two different type of dopants, each having a single level, then I will have ND1 and ND2. And in that case, again, the same expressions, I will extract an EF and calculate everything from this point, right? And why do I have two over there? Is this degeneracy factor? Because they are talking to the conduction band. If I wanted to talk to the valence band via co-doping, then each of them will carry a factor of 4. So, now the next point I want to talk about is heavy doping. What is heavy doping and light doping? I already said that the number of typical dopants, the typical amount of doping is 10 to the power 17, maybe 10 to the power 18 per centimeter cube. Number of atoms, 10 to the power 22. One atom in a million hosts. So you see this, think about it, how the proportion, this Lafayette has how maybe 250,000 people, and you are only one foreigner. That's, let's say, and then multiply it by a factor of 10 or so, that is how dilute even a reasonably doped semiconductor is. Very, very few. They don't even know about that there are other foreigners or other dopants around in the whole area, so far apart. Therefore, I already mentioned that they each have a discrete level, where only one can sit, two cannot sit because of the Coulomb interaction and everything. You know that. However, assume that in modern, especially in source drain of modern MOSFETs, the doping level can be as high as 10 to the power 20 or even sometimes 5 times 10 to the power 20. Very high. And almost every 10th or every 50th atom one could be a donor. Now, in that case, you see, the donors I have shown here with the green levels, right? Now, typically, and the three ones with the multiple color, those are host atom. But now the donors are close enough that electrons can jump from donor to donor without first going through the host atom. They're close enough. And that's why you can see the green level, if they were completely isolated, they would have two green levels, just, one in the bottom, one in the top, two levels, because they keep to themselves. But now, because they have a neighbor to whom they can go to, therefore, that level has split. Have you seen that each band now, each green band has been split into two because it has a neighbor to which it can go to back and forth. So it is sort of forming a band of its own, you see. Compared to a band of the host, it is sort of a band of the donor or the band of the dopants. So what will happen is that in typical semiconductors, if I have a EK diagram like the one shown in the right hand side, you know this, right? The density of state as a function, or the EK diagram over there. In addition, what you will have for the case in the bottom is you will have some additional states near the edge of the conduction band, shown here in green, and edge of the valence band, shown here also in green. And this is because the donors are talking among themselves. And as a result, the band has essentially narrowed a little bit, see. So this is something, these are called band tail states, because they stay slightly below, but now there is a continuum, because the donors can talk among themselves, but fewer, right? Donor atom is still 1/10, 1/100th. So therefore, it's fewer than the normal density of state, but no longer completely negligible, no longer just one level like a trap that I have shown you, or a dopant as I was showing you before. This EG1 and EA1, remember those levels? Those levels no longer one level. It is a continuum now. Okay, so what is the distinction? The distinction is that there is a difference between band transport and hopping transport. And this is how. If you take a normal semiconductor which is lightly doped, 10 to the power 18, let's say, then the electron generally jumps up. Oh, so first point is that because, let me come to that point in a second, because the levels, the gap has essentially narrowed because of the green states now. The band gap is no longer EG. It's a little bit less. When light comes in, shines on it, the jump will be a little bit less. And so the first thing to check, notice, is that the law of mass action, P multiplied by N, is no longer the band gap of silicon, 1.1 eV, but rather it is the effective band gap, another effective. And it is EG star. And the EG star is that the green, top of the green and the bottom of the green for the conduction and valence band. That reduced levels is the effective band gap. And so you will see all your relationships will change a little bit. Yeah, not completely, will change a little bit. But also interesting is this, the properties of how carriers move along. So when you have a normal semiconductor, electrons donate to the conduction band and electrons go through the conduction band. It is like highways, right? We go on to 65, we take a local exit and get to the highway, and that is how we go from city to city. There's no local road per se, right? But if the donors are sort of dense enough, and if there are a local road around, then you see what it will do, it will jump from atom to atom to atom without ever going to the conduction band. I mean, you can go to the Indianapolis by taking the local roads also, right? Without going through the highway, if there are enough cities. So these two types of transport, band transport and hopping transport, are very important. Now, if it were, I was teaching it 15 years ago, I wouldn't even have mentioned this, because electronics was all about band transport. Silicon, your Pentium, or at that time, whatever version of computers Intel had or other companies had. No longer. Because this type of transport in modern solar cells, right? If you go and work for, let's say, any solar cell company today, they make, the solar cells are made of not crystalline materials. They are mostly made of amorphous or microcrystalline material. And most of the groups now in Purdue, their research is gradually focusing on this. Energy is a big thing these days. And in those materials, transport often is not via the band, but rather through the localized states, hopping from one side to another. And the properties of transport, how it occurs, you will learn it in more advanced courses. But at the very least, you should know this because that's very useful and relevant for the devices that we are presently interested in. In fact, your flat panel displays, the things that you go buy, this 46-inch, 52-inch, the pixel, each one of the pixels is driven by transistors that are most of the time made of amorphous silicon, which doesn't have a crystalline property. And in that case, transport could often be through a hopping transport. The organic, also electronics, hopping transport. So lots of parts of electronics is actually being governed by this type of transport through the green states. Okay, so few more things. Now, so that is what I was trying to get to in the previous slide, that remember they have shown you this slide before. In the beginning of lecture 1, I wanted to wrap it up on this side. I emphasized how beautiful the silicon substrate is. Look at that. Every atom in its place. And this is just one part. And these are essentially how far apart? On the order of a few angstrom apart. And think about a 12-inch wafer. 12-inch wafer, this type of periodicity. I mean, this sort of is unbelievable that what people can do in terms of crystalline structure. And that's why you have Pentiums at this high speed in a silicon transistor. But of course, there are materials which are amorphous oxide, random material, and then there are polycrystalline material. Now, what you have learned so far translates to these materials. So first of all, let's talk about polycrystalline material. And let's think about the fate of an electron going like that. So in the beginning, let's say it was, just to make an argument, 100. Then a little bit in the middle, it goes through 111, let's say. And then a little bit later, it goes through 210. Let's say in various directions it's going. Now you know that the band gap at different directions is different. Do you know that in crystalline material? Along the L direction and along the X direction, the band gaps are not the same, are they? Right? So therefore, on its route, going from one side to another, the electrons will see a variable band gap as it is going through. No sharp band gap. And therefore, what will happen, that there is no notion of one single band gap anymore in this particular case, but rather you will have the electron will go through, every time it goes through a grain boundary, it will get scattered because the band gap has changed. And as a result, the transport will be a little bit more difficult. But the notion of a band gap still exists, the density of state still exists. It is just that the band edge is a little bit more amorphous, right? I mean, not clearly defined anymore, depending on which direction you are coming. So it is sort of the band gap for different electrons coming from different directions, the band gap will essentially look isotropic on the average. And there will be an increase in scattering. But apart from that, everything is just like silicon. Now, what about the final point about amorphous material? It's very important that we understand this. In the top side, I have shown amorphous regular structure. Now, in the homework, I asked you to look at the structure on the top, where you view the silicon crystal in a various angles. Do you remember the nanohub exercise? And so it is a periodic crystal and let's say tetrahedral structure. You can take a look. and the atoms are where they are supposed to be. I have flattened in A and D case, I have flattened it out, the three-dimensional structure. So you can see the regular periodic structure. And we have solved the chronic penny model, and we have defined the band gap and everything, and we know how, we have all these discussions about calculating the number of electrons and other things. Now what happens when you have an amorphous material? Now many people call amorphous material to be random material. Not really, because if you look at how the amorphous material shown here in section B, in the very bottom on the left-hand corner, left-hand column, you will see that the distinction between a regular crystal and the amorphous is not very much. In the amorphous case, sometimes you have a ring of 5, sometimes you have a ring of 3. In the regular case, you have always a ring of 4, but you never have a ring of 8. Or so it is a little bit, amorphous is a little bit away from the periodic crystal, but not dramatically so. That is why even in amorphous silicon, right, or amorphous silicon dioxide, band gap is still a completely valid concept, right? So this statement I want to emphasize, because most people leave this course with the assumption without understanding this final statement, that the periodicity is sufficient, right? Periodicity, if you have a silicon, germanium, it is sufficient for band gap, development of a band gap. But it is not necessary, because even in an amorphous silicon like this, so long the structure is approximately periodic, you will have a band gap. If you didn't have a band gap, you couldn't look out of the window. You see, the reason you couldn't look out of the window, because the window is made of silicon dioxide, right? It's a form of glass. Now it's an amorphous material, of course, because it was randomly processed, and it's an amorphous material. Light still shines through. That means that there must be a band gap, otherwise how does the light come through? Now if there is a band gap in an amorphous material, then surely band gap is not a property of silicon alone, you see. So this is a very important point that you should not miss. Simply because you used chronic penny model and other things, we shouldn't assume that that is a requirement for band gap, density of state, semiconducting properties. None of them are consequence of periodicity. Okay. So let me conclude on this. So we started with the charge neutrality condition on a uniform semiconductor, and from that we obtained the Fermi level. That's simple equation we had. We obtained the Fermi level, and once I know Fermi level, I know everything else, NP, number of ionized donors and acceptors I know. Now, the point I wanted to make, that all the discussion I had was for a field-free region. Didn't have any electric field. If I had that, then this condition of charge neutrality, then the condition of this law of mass action, NP is equal to Ni squared, all those have to be thrown out of the window. Not completely thrown out of the window, have to be modified. And then we'll have to use something called a Poisson equation instead of the simple equation we had to calculate electron and hole density. Slightly more general, and we'll see that. And finally, I wanted to emphasize the heavy doping effect and amorphous structure play a very important role in modern electronics that wouldn't be relevant probably 20 years ago, but now fundamentally important when you graduate and look for a job. Okay, thank you.